Welcome back to Introduction to Machine Learning. I'm Ludwig Brotmann, and in this video I will speak about properties of loss functions. We will cover some statistical properties, but also speak about robustness and optimization and cover some fundamental terminology. A loss function, as you hopefully already know, is designed to measure errors appropriately. So usually we say a loss function is L and is a function of the true target y and some model f in which we plug in the features x. And from a statistical perspective, we can, and we will do so later, make up some connections between losses and statistical distributional assumptions. So for example, we will see that assuming an L2 loss is very much the same as assuming that y given x is Gaussian. So the usual linear model that you know from statistics can also be written down via an L2 loss. And we will do more on this in the maximum likelihood versus ERM chapter later on. Losses hopefully are robust, or it helps if they are robust against fitting to outliers. So some losses, such like the L2 loss, are not that robust against outliers, which means that one single outlier can affect the L2 loss very harshly. But the L1 loss, for example, is more robust, and we will see other losses later. And fourth point here is optimization properties. These losses, or several losses, differ with respect to how complex it is to actually find the minimize of the empirical risk. So this is a good point for you to check back if you still know the difference between risk and loss. Now that you had time to think about that, the risk is the sum of the losses, or the average loss, so which means that loss measures how good a model is with respect to only one observation, and the risk measures how good the model is in its entirety, or let's say over all the observations in the data set. Right now, I said losses are usually written down as loss of y and f of x. But we can also write down losses with one argument only. For several losses, it does work for all of them, but for several losses this works, and for the most interesting ones it does definitely. We differentiate between regression losses and classification losses. That makes life a little bit easier. Let's start with the regression losses. These often depend only on the residual, which is the difference between the true target and the model. And you can see one example here on the left-hand side. This is the L1 loss, so the absolute loss, it's just the absolute value of the residual. So yeah, it's a function just of the residuals. On the right-hand side, you see some classification losses, and all of those that are plotted here can be described in terms of the margin. The margin nu of x is the product of the target and the model. And let's have a closer look on that. First, clean the slide here. If we speak about margin, then we should use the convention that the target is encoded with -1 and +1. So not 0 and 1, but -1 and +1, which means that if the margin is positive, then the model is on the correct side, right? So if the model predicts some positive score here and the true target is also positive, that's good. If both are negative, that's also good, because then we are classifying the negative class correctly. But if the signs are different, that's bad. So if we compare residual-based losses and margin-based losses, then hopefully it now makes sense to you that when looking at the residuals, we want them to be 0, right? I want to have small residuals, but we do not want to have small margins. A small margin basically, or a margin of 0, basically means that the model f has to be 0, because y can only be -1 and +1. And f, the score, tells us about the confidence of that model, right? So if the model is very inconfident, it's basically perhaps doesn't really have an opinion about that prediction task, is very indifferent, it just knows, just doesn't know, but that's not too bad. It gets really bad if we are here on the left hand side, if we are predicting the wrong class and are very, very confident that that's correct. That's the worst part, and it gets better the further we get to the right hand side. So if we classify correctly and are very confident about our prediction, that's a good thing. Let's clean that up again. Here you see 5 different losses. We treat those losses more in depth in a separate chunk, but you already see that, well, they behave quite differently, right? So the 0-1 loss apparently isn't even continuous. There is some very weird thing going on with that loss here that even goes up if we are going above 1, which is weird, right? Because that should be a desirable place to be. But yeah, let's see more about that later. Let's now speak about some basic properties. Symmetry is, well, I guess more or less obvious. If the function L is symmetric in its argument, then we can swap target and model, and the outcome is the same. For example, here we have the Breyer score, which is symmetric. It's also a function of, well, it's not really the residual, right? But it's the difference between prediction and target. But we can just switch those two and nothing interesting happens there. The second property would be translation invariance, which means if we take one real number A and we add this real number A, the same number, to the target and to the model, then the loss shouldn't change. That holds for all residual-based losses, such as for the L2 loss, for example, because this A and that A, they go away with each other, right? And as third property, we have distance-based loss functions. Always when we can write the loss as a function of the residual, so a function of R for some function that goes from real numbers to real numbers, and a 0 if and only if the residual is 0, then this is a distance-based loss. L1 is one example. It's the same plot you have seen on the other slide. It's really just based on the distance. Also, of course, the L2 loss has this property. Okay, let's speak about robustness now. There might be some outliers in the target Y. That's important because we could also speak about outliers in the feature space. We don't. Right now we only speak about outliers in the target space. So we are in the regression context, and we could say if an observation is a large residual, then it's an outlier, or a large absolute residual. Could also be a large negative number, of course. And then some losses are more robust than others. For example, the L2 loss, which you have here, that one increases very fast at some point. Okay, so first it's perhaps below the L1 loss, but then after one it definitely grows superlinearly, so faster than the linear loss. But there are also sublinear losses, which means they grow not as fast as a linear function. Okay. Here we only have one example. As I already said, we have a different chapter on all those loss functions. We will just look at the Huber loss here. So in the table, the residual y minus f, the L1 loss, which is the absolute value of the residual. Here all the residuals are positive, so it's just the residual. The L2 loss, which is the square of the other thing. And then we have the Huber loss. The Huber loss is a combination of L1 and L2 loss. As you hopefully might see here, in the area between minus epsilon and plus epsilon, it's the L2 loss. And then after that, it grows linearly. So it's the parabola here, and then it grows linearly. And well, I didn't plot that so nicely, but you will see later that the derivative at this point here from the left and the right hand side is the same, so it's continuously differentiable. So it kind of is a trade-off between the L1 and the L2 loss. As you see here on the right-hand side, we have one extreme outlier in Y, which here in that case also is an outlier in X, right? But that's not the important point here. The important point is that it's really far away from, well, from any regression line you would draw up here perhaps. And the L2 loss is affected most here. So it's really picking up on that one observation. But the Huber and the L1 loss don't. They are quite robust here in this example, and also in general they are definitely more robust than the L2 loss. As last property of losses, we have some optimization properties, and especially smoothness and convexity. Let's speak about smoothness first. We measure smoothness by the number of continuous derivatives. So this number can be 0, and perhaps when we say, well, if it's 0 times a continuous differentiable, then it's at least a continuous function. The higher this number gets, the easier perhaps is the optimization, because we have more options for optimizing the empirical risk. If the loss is not differentiable, then we have to use derivative-free optimization, which also can work. We can also use some subgradient methods, for example, for the L1 loss. But it gets even worse if the loss function isn't even continuous, right? Like the like the 0, 1 loss here, that thing. Yeah, that's not continuous. So, well, worst case, and that's the hardest optimization. We'll see later what we can do about that. Please note that the smoothness of the risk is of course influenced by the smoothness of the loss function, but inside the loss function we have to plug in the model, right? F of x. So the smoothness of the risk function not only depends on L, but also on the model. Yeah, and here is just a summary of what on the left-hand side. We have some losses that are continuously differentiable. There is one, the hinge loss, which is continuous but not differentiable. And as already said, the 0, 1 loss is not even continuous, so worst case scenario here. Second property that helps for optimization is convexity. Here you see the definition of convexity, just to make sure we're here on the same page. One small example, so this perhaps quadratic function is of course convex. Why is that the case? Because if I take two values here, which should be theta and theta tilde in that case, and I take a convex combination, so some point inside that interval, and I look at the function value of that point, then this should be smaller or equal to if I take the function values of those both here and take the convex combination here. So hope you can see it somehow. So the x, the blue x, is below that straight line I drew there, which is then the right-hand side here. If this thing is not, if this is a strict inequality, then we have a strictly convex function. And the good thing about convexity is that if we have a convex problem, then all local minima are also global. So if we find the minimum of a function, and we know that the function is convex, then we also know we have found the global minimum, which is great, of course, because one problem of empirical risk minimization, especially for deep neural networks, is this multimodal problem that we have a lot of local minima that we can get stuck in. Strictly convex functions have at most one global minimum. They don't have to have a minimum. I guess you might come up with a function that is strictly convex and does not have a minimum, but I leave that to you. If we know that if the empirical risk is twice continuously differentiable, then the empirical risk is convex if and only if the Hessian, so the second derivative, matrix notation, is positive semi-definite. And of course, all this holds for arbitrary functions, not only for risks, but also for risks. As already said, the convexity well, no, I didn't say that. I said it about the smoothness, but it also holds for the convexity. The convexity of a problem of the empirical risk depends on the convexity of the loss function, which usually is given in most cases, but go some slides back and then find out the loss function that is not convex, and on the convexity of the model, which is less often given. So if it's not given, it's a problem for convexity. But if we use an exponential family distribution, we always get convex losses. That's a good start. And if the model is linear, which is a convex function, right? Not strictly convex, but convex, then the regression, the resulting empirical risk minimization problem is also a convex problem, which means that all GLMs, so generalized linear models, all of these are convex, which then again means that every local minimum is also a global minimum. I teased very shortly that for deep neural networks we have this problem of multimodality, so that there are a lot of local minima. Here you see some loss landscapes of neural networks from this paper here. This thing here is actually convex, but the others are not, right? So you have especially here the VGG 56, but yeah, well, also the VGG 110. There are so many local minima and it's so hard to find a global minimum. That's one big problem, definitely, of deep learning, which we will, kind of sidestep for the next several chunks, but I guess we will come back to this later.